So I'm a final year PhD student here in the south of Brazil, and I'm going to present this talk here about using near-infrared to study the gas kinematics of agents. First of all, I'm going to talk a little bit about the team, the project and the team. The project, this work I'm going to present lies within a bigger project that is part of the second Large Alumni Program, Brazilian Large Alumni Program at Gemini. The collaboration is called ionized. Here is the website in case you want to check the other publications. And the main selection of these agents were they are very nearby super galaxies, very low redshift, with considerable X-ray luminosity. So these are the main selection criteria, and of course being observable at Mauna Kea. Here as a selection of field works that the group did on the whole sample or parts of the sample, but there are a bunch of other papers published prior to the definition of the sample with individual sources studying the near-infrared, especially K-band of these galaxies. So a motivation for my work, probably people that study agent feedback have seen this cartoon thousands of times, but it is very good to illustrate what we are trying to do. This is the luminosity function of galaxies, luminosity function, the number of galaxies at a given luminosity beam. And there is a discrepancy between the observed luminosity function and the predicted using just cold dark matter models that do not account for agent feedback. We understand that in the brighter luminosity and the agent feedback is suppressing the star formation in some way that we still don't know exactly what it is, and it is important to quantify this kind of thing. So as I said, the feedback has a bigger impact on more luminous galaxies, and it is necessary to reproduce the stellar populations and the type of galaxies and the mass of the galaxies we see in the present universe. So this is my sample, these 6 galaxies that are drawn from the bigger sample that contains 18 galaxies. So just to give you an idea, and on the left of each panel is the Pan-STARRS image, 3 band of Pan-STARRS combined image, and on the right side is the continuum image taken from the K-band. So the data, as I said before, data comes from Gemini North using the NIFS, that is the near-infrared integral field spectrograph. It has all of our data has angular resolution of about 0.15 arcseconds, because most of the galaxies, except for 1 or 2, were observed using the Altair, that is the adaptive optics on Gemini North, and have about 25 kilometers per second of spectral resolution. As I said, 6 super galaxies. These are some of the information about the galaxies. They are all observed in the J and K bands. And these galaxies are among the 50% more luminous of the whole sample of agent NIFS. The method we decided to approach to study the gas kinematics was to study to fit each emission line with different Gaussian components and trying to disentangle these different kinematical features. So this we used this code called IF's cube that is public. In case you want to try it in your own data cubes, you can download it. You can look for it, it's free. So here is an example of the A2 emission line, one of the brightest molecular hydrogen lines in the near infrared in the K-band. This is for one of the galaxies. Of course, black is the observed spectrum, red is the model, just one Gaussian curve. And this is the hot molecular gas at about 2000 K. These are the ionized gas. We selected the Paschen beta and the IR2022 emission lines because they are the brightest. The bracted emission line is a layer. It's not as bright as the Paschen beta, so we selected the brightest emission line to have a better signal to noise. And in this case of this particular galaxy, two curves are fitted. The purple curve corresponds to the outflow, and the green curve corresponds to the disk emission. So different phases of the ionized gas. Also, the BLR component was fitted to the CFR ones, but we just dropped it off because we were not interested in the BLR component. So an example of a fit, this is in C3227. This is for the A2, flux, velocity, and velocity dispersion. And we compared this with previous symphony data that has a higher angular resolution, and it's they have a remarkable resemblance. We have this disturbed pattern here in the center. There's a rotation, but it's disturbed with higher velocity dispersion. And then we did the channel maps, accounting the flux in different velocity beams. As you can see here, we have these features here that correspond to that disturbance that we interpret as a compact outflow based on our model of the gas kinematics, a simple rotation model. We modeled the velocity field, then subtracted this model from the observed field, and have this panel here where we see this compact emission, and this is consistent with a previous paper that observed the CO32 emission that found the same nuclear compact outflow in this galaxy. So we are tracing the hotter phase of that cold gas outflow. We also find signatures of gas inflows in this galaxy here. As the same technique with the models, we see this streamline going towards the center, and also on the channel maps, we see our more compact emission and this streaming motion that is going towards the center of the galaxy, especially this extended part here. The fraction of gas in ionized outflows was another thing that we accounted in this galaxy. It is remarkable that the ionized outflow, the ionized gas in the central 100 parsecs is all on outflows. In this galaxy, in the others where we fitted different components, we could also see that 84%, 46% and 42% of the gas in outflow, that really high fractions of the disturbed gas in the central 100 parsec of these galaxies. So my summary and conclusions, the ionized outflows traced by this broad component are seen in 3 galaxies. Molecular solid by this broad component, and in 1 galaxy that I showed before, all the emission broad or narrow component is tracing the outflow. Molecular outflows are seen in hot molecular outflows are seen in 4 galaxies. 2 of them are identified by no rotational components, this broader component, and 2 from the residual velocity maps that are confirmed by the channel maps. Gas inflows in 3 galaxies, But one important thing is these inflow rates we measure are lower than the accretion rate at the current AGN luminosity. So they are not enough to feed the AGN. And the mass outflow rates measured from the ionized gas, because from the molecular gas, they are very, very small. They are higher than the accretion rate. So the ionized gas is disturbed in the central kiloparsec. But the important thing is that we are only measuring the mechanical part of the outflow, and we are not seeing the cold gas. That if we accounted for the mass of the cold gas, things would be different. And so a few highlights on the future. NIFS will be decommissioned from Gemini North in a few months. NIRSPEC will provide similar angular resolutions as NIFS using Altair, so we will have this kind of data. Of course, MRS will be amazing to trace in the warm A2 that we plan to do with other galaxies in the future. And there is this other instrument that GMT, that this will be the successor of NIFS, that will be also amazing. So I think I reached my time. Thank you.
Thank you very much. Excellent presentation. And would anybody like to ask another quick question here? And Christina, you have your hand up, but you've got the floor.
All right, thanks. Marina, thanks for the talk. Very nice work. I was wondering, so the outflow that you measured in the molecular phase, I mean, you see them when you subtract the model, but for example, from feeding when you feed the Gaussian, the emission lines with Gaussians, do you see broad components or not? Because in the example that you show, it was only one Gaussian.
That case, we tried to fit more than one Gaussian in that specific galaxy, but it was really, really hard because the emission is really small. On the outflow, it's really small. So we tried to see if we could see another things, because that disturbed pattern remained in the central region. So we had identified the outflow by building the rotation model and then subtracting it, and we believe it is an outflow because we checked with previous literature and the cold gas and other things that indicate it is there, but we didn't fit another Gaussian to that. We tried, but we didn't reach a reliable result.
But in the other galaxies that you didn't show the lines also? That it was
only in one of the galaxies, and you see 5899, we could we fitted a Gaussian to the a broad Gaussian to the A2. There is a compact outflow seen, and on Markarian 607, we interpret it as a equatorial outflow that I didn't have the time to show all of the maps, all of the results.